Okay, let's get started with the chapter 10 lesson. And it's about correlation and regression. Let me just kind of introduce you what that is. We're going to measure two variables on each individual. So the two things that we measure, one's going to be an independent variable, which is the x, and the other one's going to be the dependent variable as the y. And they're going to show up as points. As you can see here, we're going to do problem 1, which is hours and scores. So the hours would be like the hours studied, and the score would be the eventual score. So you get a 4 and a 78. So 1, 2, 3, 4. Let's just go 50, 60, 70, 80, 90, 100. So 478. This is 50, 60, 70, 80. So 478 would be plotted as a point like that. And if we could plot all these points here, and you get something that might look like this, which basically says as the hours of studying increase, the scores are also increasing. Okay, so here we consider a scatter plot to determine whether a correlation exists and whether a correlation is linear. So as you could see here, it definitely exists. If an association does not exist, such as like shoe size, maybe we're going to measure their IQ. So we're going to get everybody's shoe size and IQ. It would probably look something like this. So if an association does not exist, we would expect to just see like a blob, like no pattern at all. But since this one is kind of trending up, there's definitely an association. Now there could be an association like this too. I mean, that's an association also, because you could see some sort of form, but in this case it would be not linear. Linear means that the association is in a line, where this one you could see is trending upward in a line. So this is linear. Okay, we also call this a positive or a negative association. Means that as the x's are getting bigger, the y's are actually falling. So that's a negative association. Okay, so that's what chapter 10 is basically about, these associations. Okay, so that was scatter plots. We got that. The correlation exists, somehow associated. So you can go ahead and read that. Means that you're kind of seeing a pattern on a scatter plot. Okay, a linear correlation, okay, would be a linear pattern. That just means that it's increasing, the y's are increasing about the same for every one increase in x. Not linear would be something like this. Hey, they're going up a little bit. Then when you get to like this x right here, all of a sudden it shoots up real fast. So that's a nonlinear. Okay, now R, the linear correlation coefficient, this is very important. This R measures the strength. Okay, and we'll talk about that here in a second, but I'm just going to give two scatter plots that are both increasing about the same. So that's increasing linear. Okay, and this is increasing linear. So both of these scatter plots are increasing linear, but which one do you think looks stronger? I'll call this scatter plot 1 and scatter plot 2. So try to come up with a decision about which one do you think is stronger. And if you went with 2, you're right. Now it's stronger because they're all packed up closer, so there's a better association here, a stronger association. Where here, it's a decent association, but they're just a little bit more spread out. So the way that it works is you're going to run the data, which I've already preloaded this data in. We're going to run the data and we'll be able to find the R. Okay. Okay, so R is closer, strong. So go ahead and read this sentence real quick, because they're going to give you this R. So R equals something like 0.92. If R is close to -1 or 1, usually indicates a strong. So this would be a strong relationship, linear relationship. Okay. Or if R is close to 0, that means a weak. So the closer it gets to 0, remember R is between -1 and 1. So if you look over here, here's -1 and here's 1. It's allowed to be this. 1 is a perfect straight line going up. This R is 1. R of -1 is a perfect downward. So that's R of -1. So 0 would sort of look like this. So when you get something like this, that's an R of 0. Okay. And I just answered the next question. A perfect relationship, R would be either 1 or -1. Okay, so notation, the number of pairs in the sample is n. Linear correlation coefficient, we call that R. And a linear for a population, we call this rho. So it's sort of similar to mu and x bar. P goes to P. Now we have a rho goes to R, but this is the one we're going to be dealing with more. Okay, so we're going to be interpreting, is there a linear correlation? So whenever we test for a linear association, the assumption is we always assume there's no linear association. Well, if there was no linear association, when you run it, you should be getting an R very close to 0. Like we just said, a R of 0 would just be like a blob. So this is going to be our assumption. Okay, so then we're going to run the test, and the test is going to give us an R, and it's going to give us a p-value. Now here's your null. This is rho, but you could just think of this as R for now. Rho equals 0. This means that there's no association because you'd get an R of 0. And the H1 would be rho is not equal to 0. So this is no association. And this is yes, there's an association. You could usually just tell by looking at the scatter plot. I mean, if you get a scatter plot and it looks something like this, okay, that doesn't look like that. That looks like this. So the p-value should be 0 for that one. Okay, and you'll see what I'm talking about when I'm doing these. So let's go ahead and run through an example showing how we could tell if there's a linear association. So I preloaded this data, so go ahead and pause the video and put this data in StatCrunch. And all of our buttons that we're going to be pushing are all this regression. That's what we're looking for. Stat. We're looking for regression. And then simple linear. That's it for chapter 10. That's all you're going to be doing for all of the sections. Okay, we want to select the x variables, variable 1. I've already have these put in already, so you need to make sure they're in there. Okay, we want to stay off. Okay, we could keep this. We could keep this. So with this, we're not worried about the intercept. We're worried about the slope. We want that slope to be 0 and not to be not equal to 0. And you're going to pretty much, it's going to be this setting every single time. You don't even have to mess with it. Now we're looking through this. It seems kind of confusing, but this is the R. And that's the p-value. So we always use the one that says slope. Those are the two guys we're going to be looking at. So our R is going to be 0.912 and our p-value is going to be 0.0114. We want to compare the p-value to that. Is there a linear association? Okay, so what I'm going to do is I'm just going to take a quick look at what the graph looks like, and you could just tell what the graph looks like right here. There you go. So you can see it does kind of trend upward. it trends upward and it's pretty linear. So we're going to say yes, there's an association. And the reason why is right here. If the p-value is less than or equal to alpha, there is a linear association. If the p is greater, there is none. So that's the link doing these. So in this case, I had a p-value of point. Let me go back and take a look one more time. It's my p-value. That is less than . So we're going to go with this. If there was no association, when I looked at that scatter plot, it looked more horizontal than diagonal. So that's a yes. This is what it looks like, but you don't have to really worry about this. This is what you have to kind of worry about. Okay, so let's do, I'll go ahead and run through a test. What I'm saying is I might pick problems that look more like this than like this, though I'm going to show you how to do it, you know, in here. We'll run through a couple. Okay, so take a second and put this data in the StatCrunch. The good thing is when you're doing your homework, you could upload it. You could upload the homework real fast when you're in there. Okay, I'm back. Okay, so me personally, I just always like taking a look to see what this graph is doing before I really get into the new numerical aspect. I always like taking a look at the picture. So this is always regression, simple linear, and compute. That's always going to be the steps. Just going to take a quick little picture, and this doesn't really look that great. This doesn't look that great, but this one guy over here is making this thing go up here. So I suspect my R is not going to be that big. It's not going to be, you know, that high. And here, 0.49. Okay, I mean, that's pretty much how you run these tests. You just have to know what you're looking for. So I'm looking for this guy right here. Looking for that guy right there. They want us to write this, but that's the test statistic. That's the p-value. That's what's making our decision. Okay, so test the claim that there is a linear correlation. So the test that there's a linear correlation, that's going to be here. If there's a linear correlation, then the row would not be equal to 0. And this row would be equal to 0. This means there is an association. This means there's no association. So the claim is actually that there's no association. Okay, find the linear correlation. I'm just going to try to create some room real quick if I can. Okay, I'll keep it like that. Okay, so the R here is going to be this 0.49. I know that's sort of in between the 0 and the 1, but that's pretty low. The test statistic is 1.38. That's your T, that's this right here. And your p-value is 0.2174. Now we need to decide on the null. Now this 0.2174 is greater than 0.05, so this is a fail to reject H null. So what that means is I'm not rejecting this. And if you listened before, this means that there's no association. This is no, I'll just say relationship. That's no relationship. So the conclusion is there's no evidence or insufficient evidence of a relationship. Between salary and viewers. Essentially what they were saying is if somebody gets paid more, they should bring in more viewers, but according to our scatter plot and our data, we didn't find that. Okay, so that's one full go by to do there. Okay, let's look at 10.2. So once we figure out that there's an association, really the main goal here, is to model this equation with the line. And that line should be kind of centered around the scatter plot. Now, going back to your algebra days, a linear equation from algebra looks like this. Y equals mx plus b, where this is sort of like your b. The b is where it crosses your y-axis, and this m is the rise over run. Just to kind of remind you, it's like here's your rise. Sorry, that's your run. So this is your run. So the run is the x increase, and this is your rise. So it's that divided by that, and that's your slope. But in statistics, we just do a little bit different. We do the y value equals a plus bx, where now this is your slope and this is your y-intercept. And it's fine because StatCrunch is just going to find this. So we just have to learn how to use it. It's pretty easy to do it. So I'm just going to kind of go over that first example we did, which was study time and scores. So what we want to do is determine first, is there a relationship? Is there a linear correlation? Question marks. So then you have to do what we just did from 10.1. If that answer is a yes, then what we have to do is we have to get the, we call it a regression equation, or least square regression line. There's a lot of names for it, for this equation right here. So we have to get the regression equation. In StatCrunch we'll find that. And the third thing is we're going to use that equation. We're going to use the equation to predict y's. So somebody could come and say, hey, I studied 8 hours. It's like, okay, well, what do I do with that? Well, you go to StatCrunch and you get your equation. So let's just pretend StatCrunch gave me this, and you take this and you plug it into that x, multiply it to the b, add the a, and that's going to give you the score that you're predicting the person to get. Okay? Now, something that's important that I'm just going to talk about real quick, so you kind of have to pay attention. If this is a no, so what I'm saying is if we had like a fail to reject like we had up here, this was a fail to reject up here. If you have a fail to reject, to find the predicted y's, you just take the average of the y's. So in this case, we didn't find evidence of a linear association. So since there was no association, you would just, any prediction is going to be the average of those y's. And the way you get averages is you just go stat and then summary stat columns. That's how we got averages before. Select the y's and then mean. So you could watch this again. That would be the prediction for any of these salaries. If there's no association, it wouldn't make sense to use the equation. You only use the equation when there's an association. Okay, so what I'm going to do is I'm going to kind of put these data in, and then I'll be back. Okay, I have my data in. We'll talk about that here in a second. So there are two different equations. You have the equation for the population and equation for the sample. So they use an equation a little different, but it really doesn't matter what you're using. I called it a plus bx. The thing that's important is whatever's being multiplied, whatever variable, whatever letter's being multiplied to the x, that's going to be your slope, no matter how it looks. The variable that's just sitting alone, that's always going to be your y-intercept, because they call it something different, which some books do. So this would be your slope. That's your y-intercept. Now to denote that, the y-intercept, we'll just call it what they called it, which is b0. Your slope is b1, and this is the equation of the line. Okay? The y-intercept here would be b0, a capital B1, and then you don't have to worry about this right here. All right. Technically, you don't have to worry about this stuff either. Once you run this, StatCrunch is just going to give you the equation. It's going to be more, let me say it like this. You're going to have to know how to use the equation. You have to know where to find it and know where to use it, versus, knowing what this form looks like. Okay, so basically, these are the chest sizes of some bears and the weight. Okay, so most likely is the chest sizes are getting bigger, the weight's probably going up too. So what is the regression? What is the regression equation? What is the predicted? So this is what I'm saying. The two main things you have to be good at are these: finding the equation on StatCrunch and then knowing how to use it. So I have the data in. So if you don't have the data in now, go ahead and pause and throw your data in. And what I'll do is I'm going to go ahead and run this. And it's always the same as last 10.1. It's always regression, simple linear, same thing. Just select what variables you want. Sometimes it's nice to name these things too. So it's always easier to name these. So my X was the chest size and the weight. This will help you in this section. Okay, now I'm going to run it now. Stat. Okay, good. See now the X, that's the first one's going to be your X. The second one's going to be your weight. And all this stuff's just always going to stay the same. Compute. Now, the equation shows up right here. Now, if you wouldn't have changed it, this would have said variable 2, and this would have said variable 1. But now that I have chest size in it, it makes it a little bit better. Now, you always want to come check this thing. You want this to be less than or equal to 5%. That's what we want. What this tells us is that there's a linear correlation. So once there's a linear correlation, then we could go ahead and use this equation. So I'm just going to take a quick peek at the graph, because technically you should always look at the graph first. See how nice it looks? It's a really nice looking linear increase there, and strong. When I go back and look, I'll guarantee that R is probably pretty close, really close to 1, which it is. I just took a look at that. Okay, so the regression equation would look like this: weight, which just so happens to be the y value, equals negative 227.1. Don't worry about this too much. And that's times chest size. Okay, and then somebody's like, well, what do I do with this? What is the predicted weight? What's the predicted weight? Here's the weight for a chest size of 50. So for a chest size of 50, I have to take this 50 right here and plug it into here. So I'll go ahead and do that with my calculator. Just give me a second to pull it up. Okay, I'm back. So what I'm going to do is do negative 227.1, so that's that right here, plus 11.89, open parentheses, and I want to put the 50 in there. So essentially this is predicting the weight for a chest that would have, or sorry, for a bear that would have a chest of 50. So 367.4, and we're in pounds. Okay, so that's essentially what you have to be good at for this section. So let's go ahead and start doing the next section. Or the next question, I should say. This is problem 2. Okay, and I'm going to go ahead and put the data in. Okay, and I am back. So we basically have two objectives here, and one of them is to find the least square regression line equation, and the second one is to go ahead and predict the temperature when a bug chirping rate is 1100 per minute. Okay, so let's go ahead and go through the steps here. I go stat regression, simple linear, variable 1. Now you could name these just temperature and then chirps in 1 minute. I'll do it the other way here. Okay, so really before you start doing anything on 10.2, you always have to check this p-value. You have to check this, because what this is saying, that there's no linear association. Basically what that means is when I go look at this graph, it's probably going to look like there's no form or anything. So what that means is we can't use this equation. So here's our equation right here. Let me just get a little space here. Oh, no, the equation's right here, so I can put it here. So the equation is temperature, because that's what we're predicting, equals 70.5 to, I'll just say 3 plus 0.009, and that's times the chirps. So the question is can I put this 11 in here? Well, you can if there's a linear association, but this number here, this 0.6227, is greater. That's a greater than 0.05. So what that means is that we do not have evidence of a linear association. So, and you'll see here in a second, I'll just go ahead and throw this graph on here, and I've never looked at it, and you'll see that's probably going to look like a blob or something. Okay, we don't have a lot of data, but there's just not that much there. If you look at this as a whole, forget this guy over here, if you look at this as a whole, it's actually almost trending downward. So what this guy is doing is lifting this line up, okay? But we don't want to use this prediction line equation. This equation right here is for this line, okay? And if you can see, we're at 500 and I'm at 75. So we're going to go 500 all the way to 0 and only go down to 70. Okay, so we can't use this. So if you remember earlier what I said, the way to do this is you would just have to find the average temperature. So we have to find the average temp. Now you don't really want to add all these up. You could add them all up and divide by 6, but that just takes a lot of time. So we'll just use StatCrunch to our liking. We have the data in here already, and just a reminder, we did this at the beginning of the year. Stat columns. I want variable 2, which is the temperatures. I'm trying to get the average temperature, so that's the one I want. So your answer here is going to be 77.7. 77.7 degrees Fahrenheit. Basically, it's going to be that for any x, for any chirps. I could say, well, what about 500? Well, let me use 550. What's the predicted temperature for 500 chirps? 77.7. Oh, what about 852 chirps? 77.7. So that's how it works. Okay, so be sure to check out the homework video too. I'll be doing the questions for these two chapters. So thanks for sticking by, and good luck.